If you would recall, our current topic is line integrals because we find ourselves in the midst of vector calculus. Computing a line integral is adding up a bunch of values of a dot product over a curve in R2 or R3. We have previously discovered that the parameterization of a given path doesn't change the outcome. So we evaluated a line integral over two given paths and got the two given parameterizations of the same path. So if we change the parameterization, we found out that the choice of the parameterization doesn't make a difference for a given path. So next, we move on to changing the path itself, giving the same start and finish, but changing the path in between. And I very suspiciously gave you two vector fields to make this calculation, which leads us to believe that one of them will probably be the same on both paths and the other will probably be different for both paths. And that's exactly what we found out with these four line integrals. I still haven't done the calculations. That's still up to you, but the integral of C1, the integral over C1 of f dot dr was equal to, I had to write it down because I wouldn't remember, 5/2. And the integral over C2 of f dot dr was also 5/2. So our choice of path didn't make a difference on f. But when we calculate g over both of these paths, the integral of g dot dr over C1 is equal to -1. And the integral over C2 of g dot dr is -2. So the answer is, does changing the path change the line integral? The answer is yes, sometimes. Sometimes we get different values, sometimes we get the same value. Any questions? So sometimes changing the path changes the line integral. Notice that for the vector field f, we got the same value, and for the vector field g, we got different values. The parameterization doesn't matter. We can come up with different parameterizations for C1 and C2. C1 over f, the integral of f over C1 will always give us 5/2. The integral of f over C2 will always give us 5/2. But for g, it was different. We had different values for different paths. Questions? Getting the same value will depend on the vector field. So what's going on here is we have to go to the next thing. We have to look at the next piece, and that would be the vector field. For some vector fields, the choice of path doesn't matter. For other vector fields, it does. Some vector fields are path independent. Some vector fields are path independent. How we get from point P to point Q is irrelevant. How we get from point P to point Q doesn't matter. That's irrelevant. We'll always get the same line integral. But other vector fields are path dependent. So G, the vector field G, gave us different line integrals when we took different paths. So that we would say G is path dependent, or F is path independent. So path independence is something that we'll see in a vector field. It's a particular kind of function. Questions? Everybody see that we're just starting off at the bottom and starting to change things, seeing how changes will affect the outcome. So we can understand the process a little bit better. So this raises a question. What makes a vector field path independent? What? So now our question for the day, now that we know that some vector fields are path independent and others are not, we want to know what makes a vector field path independent. So gradient fields are path independent. A vector field is a gradient field if it's the gradient of some potential function. A vector field F is a gradient field if F is the gradient of some potential function. A vector field is a gradient field if it is the gradient of some potential function. So if we have a function of x, y, and z, then the gradient of f is fxi plus fyj plus fzk. So we'd say that f, little f at x, y, and z is a potential function for this gradient field. So if our vector function, our vector field f is a gradient field, then the vector field is path independent. So this vector field xi plus yj is a gradient field. So that means it must be the gradient of some potential function. What we know is that the derivative with respect to x is equal to x. All right, let's find potential function. We can find a potential function for f, or we can show that f is not a gradient field. Let's take the information that we know. We know that the derivative with respect to x is equal to x. So the information that we have is that if the derivative of our potential function f with respect to x is equal to x, that means f at xy is 1/2 x squared plus some constant. Now we have to remember that we're doing partial derivatives. So the constant could be a constant function. So when we're integrating, the constant could be a function of y. The constant of integration here could be a function of y because we're taking the derivative with respect to x. So the constant of integration might be a function of y. Not just a constant plus c. When we're taking derivatives with respect to x, functions of y are constant. So our potential function has to look like 1/2 x squared plus some function of y. Let's look at the other information that we have. Fy is equal to y. So our potential function, if we integrate with respect to y, has to be a 1/2 y squared plus some function of x. For similar reasons. Functions of x are constant within derivatives with respect to y. Tried to write h, kind of looks like natural log. Still looks like natural log. Natural log just looks like h. Should have picked something else, but here we are. So we just have to resolve these two potential functions. And it looks like a function of y, g of y, could be the 1/2 y squared. And the h of x could be the 1/2 x squared. So it looks like g of y can be this 1/2 y squared, and h of x can be our 1/2 x squared. So it looks like our potential function will be a 1/2 x squared plus a 1/2 y squared, and then we can have some actual constant. The gradient of this function is going to be the derivative with respect to x. So x times I plus the derivative with respect to y times j. And that'll just be y times j. Questions? Now my arrows are complete. Notice that when we looked at the vector field G, we took different paths and had different values for the line integral. So it must be that G is not a gradient field. So G is 2xyi plus xy times j. So same thing, let's find a potential function for G or show that G is not a gradient field. I'm not moving enough again. That'll keep people interested. Funny, the lights that go off automatically. Say like you drive around in the dark. I don't know if this is an American thing or what, but like whole ass office buildings, just the lights are all on. Just leave them on all the time. It's not like it uses more energy to turn them on. Like it's got to be more costly to leave them on all day, right? I don't know. Engineers, they deal with that. Here's what I used to deal with. In high school, I was on the swim team. And at one point, we had to practice at this other school's pool because ours was being repaired. So what we found out that this school did was turn the pool heater off on the weekend. Just shut it off. And then turn it back on Monday morning. But they turned it back on Monday morning. At that point, the pool was really cold. And so they just turned it on full blast. So what happened was, on Monday, the pool was ice cold. On Tuesday, the pool was tolerable, but a little on the cold side. On Wednesday, it was pretty spot on. On Thursday, it was barely tolerable on the warm side. And on Friday, I mean, it was just too hot. Then they would shut it off again. So they just had the heater on full blast all week, except on the weekend. And I cannot imagine that saved them any energy. I do remember showing up for morning workouts on a Monday morning in February, pulling the covers off the pool and having to knock the ice off the cover and be like, "Oh, coach, are we seriously getting into this pool?" And coach is like, "Oh, well, the covers are off, aren't they?" Oh, well, shit. Here we go. I don't think the same thing is true with lights, though. I think it's just, I mean, I was advocating leaving the pool on over the weekend. I don't think the same thing is true with lights. I don't know. I'm not much fun here. Anyway, what are we talking about? Finding a potential function for g. So what we have is that gx, the derivative of g with respect to x, is 2x. So our potential function would have to look like x squared, 2xy, x squared y plus some function of just y. A potential function needs to look like x squared y plus some function of y, because the derivative needs to be 2xy. Derivative here is 2xy. The derivative of a function of y will be 0, and that'll give us our derivative of 2xy. Our gy is xy. That means our g of xy, our potential function, would have to have a 1/2 xy squared plus some function of x. Some function of just x. And now we see that we can't build a potential function for this vector field. G would have to have an x squared y term plus just some function of y, or a 1/2 xy squared term plus some function of just x. So we cannot construct any g that has these two partial derivatives. So there's no such potential function g of xy. So g is not a gradient field. I can see the mismatch between the x squared y and the 1/2 xy squared. I would have to see both of those terms in both, and then just some function of y and just some function of x. Question? But if we do have a gradient field and we're integrating from point T to point Q, then we can take any path from point P to point Q, and we'll get the same value for the line. Question? My remark. So what we're saying is that if we have a gradient field, that is, the vector field is the gradient of some potential function, and we have two different paths with the same start and end, no matter how funky one of them gets, two paths, C1, C2. The line integral will be the same. Doesn't matter how we get from point P to point Q, if we are walking through a gradient field, like so, if you're walking through a gradient field, then the line integral will be the same. Moreover, we calculate this line integral, I can just write C any path from P to Q. So C is any path. Then the line integral of this gradient field dot dr over any path from P to Q is going to be the potential function at Q minus the potential function at P. And now this is starting to look very familiar. This looks very much like our fundamental theorem of calculus way back from Calc 1, the first part of the fundamental theorem of calculus. In fact, it looks like it's so much, we call this the fundamental theorem of calculus for line integrals. This is the fundamental theorem of calculus for line integrals. Here's another example of us coming up with great creative names for things. What shall we call this fundamental theorem of calculus for line integrals? How about the fundamental theorem of calculus for line integrals? Great title, descriptive, perfect. Look at the structure of what we've got, and we think about the fundamental theorem of calculus, our original fundamental theorem of calculus. When we integrate a derivative, we evaluate at the boundary of our interval. When we integrate a derivative, we just evaluate at the boundary. Integrate a derivative, you evaluate at the boundary. Or we could think of this as evaluating the antiderivative at the boundary of the interval. We think of a function of a single variable f, then the derivative is f prime. If we integrate f prime from a to b, it's just f at b minus f at a. If we think about the function f in the line integral case, if we think about the function as a function of 2 or 3 variables, then all the derivatives combine into the gradient. So in that sense, the gradient is like a derivative of the potential function f. So integrating a derivative means evaluate at the boundary, which for things that are one-dimensional, that's the endpoints. How's everybody okay? Whenever we look at a new thing in math, we have to look at how this is related. We keep using the same language that we used in previous ones, in previous math classes. How is this new? What has changed? Functionally, it should do the same thing. So what's changing? Our functions are now functions of 2 variables. But we want the derivative to tell us which direction things are going. That slope of the tangent line in a function of 1 variable is a function of 2 variables. Which direction is this curve going? That's pointing in a direction that's a vector. And we need to call that, and that's going to be the gradient. So in that sense, the gradient is acting as the derivative of the potential function f. So we're really doing the same kind of thing. Evaluating the derivative or integrating a derivative by evaluating the function at the endpoints of the interval. Evaluating an antiderivative at the boundary. Another way we could think of it. F is the antiderivative of f prime. So we could also think of evaluate the antiderivative at the boundary. That's the big thing for this week, the fundamental theorem of calculus for line integrals. How it relates to the thing that we called the fundamental theorem of calculus before. Because if we're going to call something the fundamental theorem of calculus, there better be some parallels with what we've done before. Now all we have to square with is the fact that there's 2 other fundamental theorems of calculus when we're in vector calculus. 2 other things that have this kind of calculation involved. But the big picture, evaluating an antiderivative at the boundary. How's everybody think? It's funny because big deals in math never hit until way later. It's like this is a big reveal in a movie where everybody's going, oh, wow. But it's math. And so it doesn't really make sense when you first see it. So not until way later does it start to hit that same way. It's kind of like watching Star Trek Into Darkness, where Benedict, now that movie is old, so if you haven't seen it, the statute of limitations on spoilers has expired. But if you still haven't seen it, and you need things that need to avoid spoilers, note that I've already ruined it by saying that there's a spoiler that can be done in this movie. So as soon as you tell your friend, I don't want to spoil it for you, unless you say that for every single movie you watch, you're telling your friend that there's a spoiler in the movie, and you've already spoiled it. That make sense? Don't be like all spoiler alert unless you do that for every single movie. I went and saw Jackass. I don't want to spoil it though. No spoilers in that movie, but you have to say that for every single time. Oh, I saw the new M. Night Shyamalan movie. There are no spoilers. I don't want to talk about it. Oh, there's a twist, but you have to say that all the time. You know what I mean? I don't want to reveal the secret. Tells the person that there's a secret. They're going to be watching out for it. They're going to spot it ahead of time. So anyway, so like Trek Into Darkness, when Benedict Cumberbatch is like, "Oh, I'm Khan," right? No one cares. In that universe, no one cares. None of the characters, the audience, no one cares. He's a background character. He has to tell you why he's mad. The original Star Trek Wrath of Khan, when Khan shows up, we're like, oh shit, we knew that was going to happen because it's called the Wrath of Khan. But we already knew why he was mad. We already knew that he had a bone to pick with purpose. Trek Into Darkness, it was just, we have to believe it. So, fell flat. Hit reveal. Only until later do we find that out. You know what I mean? Big talk coming from someone who just talks about everything. Me, I'm just blah, 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 blah. It's terrible storytelling. But I guess we have other purposes. So there it is. I'm also saddled with the habits of generations of teachers. What we want to look at here is that this fundamental theorem of calculus for line integrals has a lot of parallel with our OG fundamental theorem of calculus. Integrate a derivative by evaluating the function at the boundary. That is, you evaluate the antiderivative at the boundary. Let's just expand what our notion of an antiderivative could be. All right, that's going to do it for today. I will see you all on Monday. Once again, I'm not going to be able to hold a meeting tomorrow for reasons. So that's it for today. That's it for this week. I'll see you all on Monday. If you have a good weekend. Thanks for playing.